Say you have this object that's moving along a line. And you want to track the motion of that object. I've been talking a lot about the point that before you can measure where that object is at a given instant, you have to choose a zero position and a positive direction. Okay. So to track this object's motion, numerically, you need to choose a positive direction and a zero position. So imagine that two different independent people are tracking the motion of this object. People track the motion using different zero positions. Although it's important to recognize that for this stuff, the positive directions have to be the same. So the question is, how do their different, those two measurements of position compare to each other? How do the two measurements of position compare, relate to each other? All right, well, let's say that one of these has its zero position here and its positive direction that way. Okay, I'm going to call that reference frame A. And then the other one has its zero position here. Positive direction has to be the same, and I'm going to call that reference frame B. Okay. What we want is a mathematical way to relate what the person at A sees so that the person at B could always calculate what's going to be determined, what's going to be seen from A. Okay. So to do this, we're going to use this naming convention. So the position naming convention we're going to use is that the position of, I'm going to call, well, it's a car, so I'm going to call it C for car. So position C, like fraction bar A, okay, so that's all a subscript, C over A. I'm going to call that the position of C relative to A. Okay, so that's the position that's observed to someone with their 0 position at A, and the position of C relative to B, or, C over B is what the subscript looks like, and I'm going to call that the position of C relative to B. And the relative motion equation for position, then, this is always true. The position of C relative to A is equal to the position of C relative to B plus the position of B relative to A. So the position of B relative to A is saying, for the person who's observing this motion with their 0 at A, what would they say the position of B is? Okay. So this is our first relative motion equation. And if you look at these answers, like what I drew here, say these are 10 meters apart, say it's 5 meters from B to the car. Okay. It's saying that, so this is 10 meters, this is another 5 meters, right? So it's saying that the position of the car here, observed by A, well, what is it? What's the number? It should be 15, okay? So it's saying that the position of the car observed by A should be equal to the position of the car observed by B. What's that number? 5, plus the position of B observed by A. What's that number? 10. So it makes sense that that works out, right? It's not always going to be called A, B, and C. These subscripts will have different names based on what you're tracking and whatever. So there's a memory device that'll always let you get the subscripts in the right order. And it says, think of the subscripts as a fraction multiplication. Then the order of the subscripts is right when the fraction multiplication works out. Okay, so what I have here is C over A is equal to C over B times B over A. The B's cancel. And so you know that you have this in the right order. Okay, any questions about that? Okay, well, this gets more interesting and more useful if those 0 positions are not just sitting there on the street, but they're actually moving around as time goes by. Okay. So those 0 positions can also be moving. Yes. They don't have to be. One could be still and one could be moving, or one could be going the other direction. Okay. But if you take the time derivative of both sides of that first equation, time derivative of each side of the boxed equation above you get d dt of the position of of C relative to A is equal to d dt of the position of C relative to B plus d dt of the position of B relative to A. Well, these are just velocities. So you can think of this as the velocity of C that's observed by A is equal to the velocity of C that's observed by B plus the velocity of B that's observed by A. And so there's the velocity relative motion equation. And that subscript rule still has to work. Okay, I didn't change anything about the order of the subscripts. And then you can do it again and you get the acceleration version of this. And so the last one says the acceleration of C relative to A is equal to the acceleration of C relative to B plus the acceleration of B relative to A. So those three boxed equations are the relative motion equations. Intuitively, think of each zero position as a video camera or an observer. Okay, so think of it as either a person represented by B moving around, or they don't have to be moving around, or a video camera that's moving around on like some kind of cart. Okay. Then based on what's observed by one of the video cameras or one of the observers, you could calculate what the other video camera is going to see. Okay. And one thing that's sometimes helpful is if you ever have the right subscripts, but they're in the flipped order, okay? You can flip the subscripts if you just make the whole thing negative. So I'll do it with position too. So position of A relative to B is negative position of B relative to A. Velocity of A relative to B is negative velocity of B relative to A. And acceleration of A relative to B is equal to negative acceleration of A relative to B. Okay, so let me do an example problem, and it'll sort of point out cases where, like, what's kind of the practical application of this. All right, so first of all, an elevator. So think of what an elevator does. So you get on the elevator and it's still, okay? And then it takes you up or takes you down. Before, most of the time that it's going, it's moving at a constant speed. Okay, so on the way up, most of the time you're just going like 3 meters per second up or whatever. But right at the start, there has to be a period where you're going from rest to 3 meters per second. And so right at the start of that motion, you accelerate for a second or something. And you can sense that. That's the feeling that you get when the elevator starts to move. You can sort of feel it in your stomach. That's what you're feeling is the acceleration. Okay. And then it goes away once you get up to speed. You all know what I'm talking about? Okay, so let's say that an elevator is accelerating up when a passenger drops his keys. A video camera, like according to a video camera in the elevator, it shows the keys accelerating down at 12 meters per second squared. What's the acceleration of the elevator? And I should say, for these early problems, this relative motion thing is going to be important in this class. For these early problems, a lot of you probably can just sort of work it out kind of by feel and get it right. But get in the habit of writing it out in terms of the variables and the subscripts, because you're going to need to do that later. Okay. Okay, so here's what's going on. We have this elevator. And here's the key. The key is falling. So I'm going to call the key K. The camera in the elevator, I'm going to call E. Okay. So whatever that sees, that's the measurement taken by E. And I'm going to call my positive direction up. Remember, the positive direction has to stay the same for both of your two measurements. And then I'm also going to have a reference frame that's fixed to the ground. So let's say this is the elevator shaft. You can imagine there's also a video camera that's fixed to the ground. I'll call that G. Okay. All right, well, we're dealing with accelerations, so we want to use the acceleration equation that says the acceleration of the keys relative to the ground is equal to the acceleration of the keys relative to the elevator plus the acceleration of the elevator relative to the ground. Okay, are you with me on that? And this is the one that we're trying to calculate. We're trying to calculate how much is the elevator accelerating according to the camera that's mounted to the wall. Okay, well, this camera that's mounted to the wall, even, and by the way, these can be imaginary. It doesn't say anything about there being a camera mounted to the wall of the elevator shaft. But if there was a camera mounted to the wall of the elevator shaft that could see the keys, what would it see the acceleration of the keys to be? We have negative 9.81 meters per second squared because the keys are in free fall. Okay. What's the acceleration of the keys that's seen by the elevator? Yep, and it's down, so it's negative. So negative 12 meters per second squared. And then this is what we're trying to calculate. And so now it's just algebra, and you get that the acceleration of the elevator relative to the ground is equal to positive 2.19 meters per second squared.